So, good afternoon. Let me welcome you at our last meeting of our seminar in this academic year. And it's my pleasure to introduce to you, or maybe it's not necessary to introduce the speaker. Today, we will listen to the talk of Droganova, and she will focus on the taxonomy of deep syntactic relations. So please, the floor is yours.
Hello, everyone. Today, I'm going to talk about a proposal for universal semantic role labels. We are working on this proposal with Dan, and I would appreciate your feedback so we can improve it. Our proposal is oriented towards universal dependencies. We've studied the data for 5 languages: Spanish, Catalan, Czech, English, and Finnish. And we've examined 3 linguistic perspectives because all of them have deeper syntactic semantic representation. And they are widely used in the linguistic community during a long period of time. So we examine meaning text theory, functional generative description, and PropBank. So I'll start with UD, and actually I think UD does not need any introduction here, especially after the Joachim's talk. But I do want to talk about UD a bit because I know there were some questions around enhanced universal dependencies, deep UD, and this is all related to this current proposal. So the UD guidelines define basic UD representation. Then there's also enhanced UD representation, but this representation is optional. And this means a tree bank can have some of the 6 defined enhancements types, all of them or none. And these 2 things are defined in the UD guidelines. Next, deep UD. This is a project we were working with done in 2019. It's not a part of the UD guidelines, although the data is available for all UD languages. Okay, almost all UD languages, and I'll talk about this in a minute. And then universal semantic role labels proposal. Another part of the UD guidelines, this is our current project, and this is the focus of the second part of my talk today. Enhanced universal dependencies. So they make implicit relations between nodes explicit. The guidelines define 6 types of relations. First, refers to gapping. So empty nodes for related predicates are added to the sentence structure. So here we can see that E8.1 and E8.2 are reconstructed nodes, and when we have them, we can actually say that J is the subject and a croissant is the object of the second clause. Next one, the propagation of incoming relations, so not first conjuncts. And here the enhanced representation is marked in blue below the sentence. So we can say that K is also the subject of 1. Next one refers to propagation of outgoing relations for not first conjuncts. Again, the enhanced layer represented in blue. So we can say that she is the subject of cancelled, and the training is the object of cancelled. Next one refers to additional subject relations of a controlled or raised verb. Again, in blue, we can see that I is also the subject of go. Next one refers to reference. So we can see that the institutes is the subject of wanted, and the the relative pronoun also has the specific label ref. And the last one refers to modifier labels that contain the information about the cases. So this information basically extend the main label. Now I'm moving towards deep universal dependencies here, because this was part of our work. So in this paper towards deep universal dependencies, we examined the data. It was UD release 2.4, and we wanted to know how things are with the enhancements types. And we discovered that only 24 tree banks of 16 languages have at least one enhancement type, and only 6 of them of free languages have all 6 types. A couple of years later, in 2021, in his paper, Enhanced Universal Dependencies, the Current State of in Outlook, Dan actually collected this statistics again, and it was UD release version 2.8. And it turned out that now 33 banks of 18 languages have at least one enhancement type, and 15 tree banks of 8 languages have all of them. So this data does not grow that fast. And this is not a huge surprise, because usually this data becomes available in a tree bank if this data is available in the source. And manual annotation is extremely time consuming. Now, I'm going to talk about deep universal dependencies because it was part of our work there. So deep UD is automatically derived from UD, both basic and enhanced. And as a part of this project, we created a pipeline that produced this enhanced universal dependencies for 121 tree banks of 73 languages. We needed to exclude some of the tree banks because of the license-related reasons. And our goal was to produce deep semantic annotation level. It was very ambitious, so I would say deep UD is just the first step towards this. And why do we need enhanced universal dependencies at all? So this is an example of gapping. So again, in blue, this is the enhanced representation. So when we have this reconstructed nodes, and then we can now say that the J is the subject and the cross-on is the object, and it makes it easier to move to arguments. So now we have some missing pieces, so we can actually say what are the arguments here. But we produce this enhanced UD representation, but it doesn't mean we produced all 6 types, because in some cases it was not possible. And here I'll give you an example of such case. Grammatical correctors. I say partially because we were relying on some language-specific heuristics here. And we were using some language-specific dictionaries for relative pronouns, but also we needed a relation. We needed this ACL column rel-CL label available in the data. And this was not always the case. So we could not produce this enhanced representations if a tree bank does not have this sublabel available. And our main focus was on normalizing syntactic alliteration, which is similar to this work by Candido. What we did, we wanted to to make sure that arguments are assigned properly. So in this example, he killed the dragon. He is arg1 and the dragon is the arg2. But in this example, the dragon was killed by him. We want to make sure that him is also the has the label arg1 and the dragon arg2. And in this example, she made him kill the dragon. Again, dragon has the label arg2 and him arg1. And in this example, the same, the dragon would get the arg2 label. So we produce this numbered arguments, and it can be mapped to a valency dictionary, but we didn't use it. It was not a part of our goal. So we try to keep this degree of proximity. So the subject of an active clause is arg1 and the direct object is arg2. And another thing we did, we produced the predicate identifiers. Again, it could be a frame identifier or a sense identifier, but we just use lemmas. And this is basically an extension on top of the original UD format. So here you can see it's a normal QNLL file, 10 columns, and then we added these 2 additional columns that store the information about predicates and arguments. So deep-pred is this predicate identifier, and deep-args is this stores the information about arguments. And this is the example of our annotation on top of the basic UD. So that was deep UD in a nutshell. And now I'm moving towards our proposal. So it's oriented towards UD. We studied this data for 5 languages, and we looked closely to these 3 frameworks. I'll give a very brief summary of these 3 frameworks. So meaning text theory is a 7-level representation that is focused on representation between form and meaning. And we examined the data for Spanish and Catalan. It's available in the labels are available within the UD tree banks. And we found out that there are 7 argument slots, and arguments are numbered from 0 to 4 according to their degree of proximity. Then there is this arg-m label for adjuncts, and arg-l label for lexicalized complements of light verbs. There are also 20 thematic roles that can be mapped to these arguments. And this is an example of Ancora data. This is a real example from the Ancora data. So you can see the mapping between this Ancora data and UD. Okay, FGD does not need any introduction here, I think, but I'll highlight a couple of important things. We were working with PDT and PCEDT data. We found out that there are 67 functors, and there is a distinction. So there are 5 arguments, and the rest may be considered adjuncts, and this is mapped to the valency theory. Next, the PropBank project. this is a tricky one. It has a semantic layer that is kind of maps the information, semantic information in the constituency structures of the Pentry Bank. And we were working with data for Finnish and English. Finnish data came from the Finnish proposition bank, which is built on top Finnish dependency tree bank, and we have a conversion, but it was version 0.1. So to be able to work with this data, we needed to reparse the data using UDPipe, and we produced this annotation on top of the gold tokenization, and then we propagated the information about the frames. And as for the data for English, we propagated the frame information from the original data to the PCEDT data. And we found out that there are 5 arguments numbered from 0 to 5. There is our A label, which is a very specific case for clausal agents. It goes only with verbs of violational motion. It's really not frequent. And there is this arg-m label, typically for adjuncts if they're not tightly bound to particular verbs. But also, there are 15 subtype labels that specifies semantic category, like location, direction, manner, and typically they go together with arg-m, but they also can occur with numbered arguments. And yeah, this is another example how this information, how the PropBank labels can be mapped to the basic UD example. Now, what we did, we examined all the data for all these languages, and we examined the labels and their variations, and we created mapping tables between all these 3 frameworks, and we designed this 13 top-level labels or main labels. And the main label expresses the main semantic category, but it can be also extended with a sub-label. It's an optional part, but we wanted to preserve the data if it's available in the source tree bank. So in blue, this is our how it can be mapped to, and this is the example of our label set and how it can be mapped to the basic UG representation. And you can see that some of them have this extended label and some of them don't. And I want to give you a better example. So this is an example sentence. And this is an example of a mapping between these 3 frameworks to our label set. This is the time label that corresponds to temporal adjuncts that is designed for different temporal points. So this mapping is from PDT to our label set. And that's why, like, again, I highlighted everything in blue. So in PDT, we have this information. So we are mapping TFHL label to the time label. So we can use this extension and add it to the conversion. If we want to convert the data from Ancora, and if we want to convert the TMP label, or the data from PropBank, and we want to convert this argm TMP label. We don't have this extended information, so in this case, it would be just time label. So this is our set of labels. I need to say that we loosely follow the FGD distinction between arguments and adjuncts, but we don't use valency dictionaries, and this conversion cannot be perfect because of varying definitions of arguments and adjuncts between the three frameworks. Some categories are available only for PDT, so I mark them in gray. So there's no direct counterparts here, but we just want to keep the categories for the future. And again, this is the format. It's very similar to DeepUD. Again, first 10 columns, the normal, usual kernel file, and then 2 extra columns where we store the information about predicates and arguments. But in this case, we assign the labels from our data set. Next, I wanted to talk about the complex cases, because it's not an easy task. And I want to highlight the differences and complications. So actor is the most active participant in PDT, but it doesn't have to be too active. And it has it's very similar to the arg0 AGT label in the Ancora data, and to the arg0 in the PropBank data. So this is how we map this. In this example, by Rodrigo Barra will be mapped to ACT label, although it has this arg0 column AGT label in the Ancora data. Also, it includes experiencers. Again, an example from the Ancora data. You never hear. You in this case will map to the ACT label. And also some cases of inanimate subjects. Another example from the Ancora data, which is labeled arg1 column temp. And another one from the Ancora data. It also corresponds to causers. So in this example, one camera attracts other cameras. One camera will be labeled as ACT. And also, it can correspond to the arg1 label in PropBank when the agent is not expressed. So in this case, the door open, we will assign the ACT label. But in this case, the door was open. We want to assign the patient label, but it corresponds to the, so it's really hard to distinguish between these cases. Next one, patient. So it's the participant affected by the action, according to PDT. And it corresponds to different labels in the PropBank. It's the arg1 label, and in the Ancora, it's arg1 column path label. it's one of the easiest cases. But also it can correspond, like this is what was found in the in core data. When like the cases are when the object is more abstract. So in this case, to fill jobs in various sectors, will get this path label. And yeah, and the example from the previous slide, I'm highlighting it here again because this is one of the complications. It's hard to distinguish between these cases. And also we found some cases of when the arg1 PropBank label corresponds to the affect label. So in this case, we're surprised by the move. In the sentence, GM officials said they too were surprised by the move. It's still the arg1 label in the PropBank data, and it should have this the affect label according to our label set. Next one, as we see, is the recipient in events of giving and transferring. Very similar to arg2 column band label found in the Ancora data. And typically corresponds to arg2 in the PropBank data. But we need to pay attention to the extensions here because it's not always the case. In this case, arg2 label have an extension and it corresponds to different things. In this case, it's the difference, the label designed for difference. And also arg2 PRD label typically corresponds to the patient label in our label set. Next one, affect. It's not an obligatory position, so it denotes the result of an event. This is an example from PDT. And it's similar to many instances of arg3 and arg4. And also similar to arg1, as this is an example from previous slide. And similar to arg2 column attribute in the Ancora data. And sometimes it is assigned in the cases where it's not true state changes. So to be considered a leading figure or to consider him incapable should be also labeled as the affect. The last one, origo, may correspond to the English preposition from, but it's not to the adjuncts of direction or time. So again, this is an example from PDT. OD Europe should be labeled with the ORIC label. And then this is very similar to arg2 column caught in the Ancora data. So in this example, the cells should be labeled by the ORIC label. Now, but not with the arg3 column ORI label, because this was designed for directional and temporal adjuncts, so it's an absolutely different case. So we need to make a distinction here. Yes, and as for the PropBank data, it's very similar to higher number arguments, such as arg3, and some of the cases can be distinguished by using this from extension. Now I want to summarize the information about adjuncts. There are 32 verbal adjuncts, and on the Ancora and PropBank side, there's this just one argm label that goes with different subtypes. So most of the labels are self-explanatory, but these are different levels of granularity. So how do we map all these 32 labels with this one label plus subtype? And there are multiple cases where these mappings are very challenging. It's usually this subtype information is available for conversions from the PDT data, but it's not always the case. For instance, this is an example of reciprocity. Both men seem to work well together. Together is annotated as argm reg, because this label is available in PropBank. But in PDT, this information is presented on the tetragrammatical layer. So there is no direct label. So we cannot really extract this information. So typically it has some, I think typically it has the patient label, but there are variation. I found an example when it has this ACMP label on the PDT side. And another challenge is that subtypes intended for adjuncts can actually go with numbered arguments. And yes, this is one of the examples. So you would think, okay, this is argm x, maybe it's an adjunct because this is an adjunct label, but that's not true because it's mapped for the patient label in the PDT in this example. Thank you.